In this London office block, there are approximately 2,700 people at work. Assuming that they each have a telephone, it's possible for them all to dial subscribers in another large city, say Birmingham, and in theory, to have all their conversations channeled through the same single line at the same time.
Hello, look, I'm sorry. It's absolutely appalling, this line.
Are you sure you're in Birmingham? You sound as though you're just round the corner.
Well, I am shouting.
In practice, as every telephone engineer knows, there's going to be at least one caller every day on each floor of that building who's going to have problems. At first, anyway. But of course, he can always redial. That's one of the joys of modern long-distance dialing systems, and one of the frustrations for both subscriber and engineer. There is an urgent need to maintain the quality of service. Let's take, for example, the telephone system in the United Kingdom. It's the third largest in the world, operating over 20 million telephones and doubling every 10 years. Before subscriber trunk dialing became widespread, operators could spot faulty lines and report them to the engineers.
Testing telephonist reporting no tone on Luton dial 27.
Now, in spite of automatic routinging, some of these faults may still go unreported. Meanwhile, increasing use of the trunk network, both due to long-distance and international traffic, means that the performance quality of the network needs to be carefully maintained if the service is not to suffer. Routine maintenance is becoming less common due to both the scarcity of technical manpower and the undesirability of removing operational plant from service. The increasing reliability of modern equipment has enabled telephone companies to move towards the policy of maintenance on fault. Poor transmission on either local or trunk networks is serious for both subscriber and telephone company. International business, for example, is growing at a rate of 40% per year. So what is the answer to the problem? Of course, there is no simple answer. To test the entire network regularly would be a colossal task. On the other hand, maintenance on fault requires that problems be localized and corrected with utmost speed. At this busy switching center, long-distance calls are passing through at a rate of thousands at any one moment. It would be impossible to provide the resources necessary to monitor all these trunks for quality. Or would it? An important advance in automatic surveillance has changed the picture. This is Marconi Instruments' automatic baseband monitor. Basically, it's a quality assurance device, which enables transmission standards to be maintained by ensuring that systems are always within acceptable limits. It assists management by helping to identify where problems occur. Not only catastrophic total system failures, these are already effectively monitored, but other problems which degrade the service quality. In many cases, this is the only way of finding such faults, where the size of the testing task has ruled out manual methods performed on a routine basis. Overloads can be due to excessive carrier leaks or supervisory tones. Increasing customer use of data can cause serious problems, as can wrong setting up during commissioning or maintenance. The baseband monitor quickly identifies these types of problems. Quite a step forward, but also a natural one when looked at against the way things have developed over the last century. In 1876, Marconi was 2 years old. That year belonged not to him, but to Alexander Graham Bell and his newly invented telephone. By the time that the young Marconi was at work on his early experiments, the telephone had already made enormous advances. At just the time that Marconi was dispensing with wires, the telephone system was becoming nearly strangled with them. By the 1890s, the telephone had already become a part of daily life. Meanwhile, Marconi also was fast becoming a household name. It's hard to think of two names which have had more influence on world communications than those of Bell and Marconi. From those beginnings, the move was always towards simplification and greater efficiency. The telephone system gradually solved the problems of the many wires as the concept of multiplexing was developed. The trend has continued. With the help of increasingly efficient multiplex systems, the network has developed into the efficient and highly capital-intensive system that we know today. The world of Marconi was not standing still during all this time either. Part of Marconi's original company is Marconi Instruments Limited, the largest European manufacturer of communications test equipment. They produced the first commercial white noise test set some 20 years ago. These have been developed continuously and are widely used all over the world. It is against this background that we must look at this new meeting between the name of Marconi and the invention of Bell. It is on the long-haul, multi-channel circuits where the scale of lost business really makes itself felt, when the quality of service deteriorates. Until now, test procedures have not been extensively automated. However, the economic repercussions of failure are most serious. What is needed is a powerful automatic surveillance system for application at the baseband level. So let's see how the Marconi Instruments baseband monitor fits this requirement. First of all, what does it consist of? The selective level meter, which scans FDM basebands, is the heart of the system. This interfaces to the basebands to be monitored via a filter unit and also a scanning coaxial switch. Control of these instruments is by a bus controller with associated floppy disk. In diagrammatic form, the makeup of the ABBM is seen more clearly. The fully automatic 20 MHz selective level meter incorporates built-in synthesizer tuning. The filter unit provides pre-filtering for slot noise measurements, and the two units together provide traffic measurement at all levels from group up to total baseband. Scanning is via the coaxial switch unit, which provides capacity of from 4 to 56 baseband inputs. These units are operated by a dedicated bus controller. In conjunction with a floppy disk unit, the system restarts automatically. The controller is connected to a visual display unit, keyboard and printer, which may be local or remote. The printer provides fault summaries and other reports, while the visual display unit and keyboard are used for data entry and operator intervention. With modems and a data link, they may be placed anywhere. Of course, the hardware is important, but only a part of the overall concept. The user programs, being written in BASIC, may be easily amended. However, the monitor contains, as standard, a complete set of programs which have been developed in close consultation with the British Post Office and overseas telephone organizations. These provide for both flexibility of measurement choice and ease of operation, and allow the baseband monitor to commence measurement on the very first day at a new location. The best way to understand its capabilities is to watch the operator making these initial choices, which are, of course, only necessary at first installation. The time at which a regular fault summary is required is entered. Since different automatic test modes may be selected at peak traffic times, the operator enters the standard peak times required. The test options are now displayed. Tests 1 to 3 allows selection of reference pilots at various levels. Test 4 allows measurement of noise in inter-supergroup slots and tests 5 to 9 normally allow traffic power measurements of the total baseband through to individual channel. He now has to choose the standard tests to be carried out at both off-peak and peak times. Since all measurements are compared to threshold values, he must now enter the maximum permitted power levels. Maximum, nominal, and minimum permitted pilot levels are also entered. The operator now selects the Print on Fault mode, enabling all violations to be listed as they occur, in addition to a daily fault summary printout. He now starts to enter the baseband information. First, he enters the baseband name for use subsequently in all reporting. He then selects the correct baseband plan and enters other information relevant to that particular baseband. This can then be repeated for each baseband. Of course, in many cases the data will be standard, so speeding up the initialization process. However, the system's complete flexibility could allow every baseband to have different tests, thresholds, or times if required. Having completed the data entry for all basebands, the ABBM scans each one to identify channel capacity and absent groups or supergroups. The station record ensures that automatic surveillance is only carried out in occupied portions of each baseband. It can be printed out daily or weekly to form a very useful management document. The system is now operating in its normal unattended automatic measurement mode and requires no further intervention. It is even immune to power failures, since it dumps its information regularly onto disk, and a non-volatile clock allows continued correct timing. To see how the system operates, let's look at a simple diagram. Automatic measurements are normally taken down to a selected level, say supergroup traffic level. When an out-of-limits condition is measured, it moves its attention progressively down the structure until the faulty condition is discovered. Let's return to the station manager's office to see some typical faults which can arise. During automatic measurement, the VDU is continuously updated, with faults optionally also printed out as they occur. The baseband monitor is now on input 3 and has found 3 failed pilots. On completion of pilot tests, slot noise measurements have been selected for this baseband and 2 are found to be out of limits. Traffic scanning has been set at supergroup level, and supergroup 8 of hypergroup 2 is found to be high. The diagnostic capability of the baseband monitor identifies the most likely cause as being in group 3, where channel 3 is over 6 dB above its -8 dBMO limit, and channels 11 and 12 are marginally high. Remember that neither groups nor channels have been selected for routine measurement. On completion of supergroup power measurements, we move on to the next baseband, where 2 pilots are found to be out of limits. There are no problems with inter-supergroup slot noise levels, nor are there any traffic violations observed at supergroup level. And so the monitor continues its unattended routine. However, the capability of amendment or occasional manual control are of course vital. This is initiated by pressing the interrupt keys. Currently, there are 11 options. Let's look at some of them briefly. Options 1 to 5 allow the stored information to be listed or changed. However, when troubleshooting, it's important to be able to take over manual control of the automatic routines. This is option 6. Let's see how we can investigate some of the problems identified on the fault summary. For example, we see that in Hypergroup 1 of input 7, Supergroup 8 has been found high 43 times, along with Group 3 and Channel 3. Selecting option 1 of the test facilities, the operator enters input number, followed by hypergroup, supergroup, and group numbers. Finally, he requests measurements of all 12 channels by entering A. All channel levels within the group are measured, and we see that channel 3 is still almost 7 dB above the threshold. The operator selects the option of repeating the measurements. Looking at the suppressed carrier fault summary, we can see that carriers in channels 7 and 9 of this group have been found high 43 times. Returning to the VDU, option 2 is selected in auto range mode, and all carrier leaks within the group are measured. We see that channels 7 and 9 are 20 dB and 10 dB respectively above the minus 25 dBMO limit. Using the preset mode of this option allows a complete carrier leak scan of the selected baseband, and in this case lists positions of all carrier leaks above minus 25 dBMO. Returning to the test facilities list, we see that inter-supergroup slot noise can be selected, and in option 4, reference pilots. Using Control K to exit to the user options, we see option 7. It is this option which sums up the true value of the Marconi Instruments automatic baseband monitor. FDM system maintenance is currently manually intensive. Whilst the monitor does not reduce the need for personnel, it does enable management to direct skilled and expensive technicians into areas where they're most required and can use their skills most profitably. It brings a change of emphasis away from purely routine tasks, creating higher job interest with greater prestige. Baseband monitoring within an expanding network allows management to make the best use of maintenance labor. The quality of service is maintained without the need for increases in staffing levels. All these needs are satisfied by the Marconi Instruments baseband monitor. And remember, it's working to help improve the quality of service from the very first day.